Hello, and today we're going to learn how to find the domain of a function algebraically. Let's first remind ourselves that the domain of a function is all the values of the independent variable. We usually call that x, and for today's video, all of them are going to be called x. So we're looking for every single value that's possible for the x variable. So let's look at our first example here. F of x equals x squared. X squared is a function that takes a number and then squares it. So is there any number that we're not able to square? The answer is no. We can square any number we want. So this has a domain of all real numbers. So in interval notation, we write that as the x values that are possible is everything from negative infinity to positive infinity. No number we can't square. All right, let's look at the next function. G of x equals negative 2x plus 7. So what are the values of x that we can multiply by negative 2 and then add 7 to? And the answer should be all of them. There's no number that we're not able to multiply by negative 2 and then add 7 to. So once again, here my domain for this function is that x can be any number, any real number between negative infinity and positive infinity. All right, so what happens if we have a function that has a restriction, like this, the square root of x plus 5. Taking the square root of something is trickier than squaring something or multiplying it and adding it, because you can't take the square root of a negative number, which means the quantity x plus 5, this thing, has to be positive or 0. How can we represent that? We can write an inequality stating that x plus 5 has to be greater than or equal to 0, meaning it can't be negative. And if we're just one step away from figuring out all the values of x, that would work. We subtract 5 from both sides. We would have that x has to be every number, can only be numbers bigger than negative 5 and including negative 5. So we've just found our domain. The only values of x that will work are values from negative 5 inclusive up to positive infinity. You can do a quick check. Take a number outside of the domain like negative 6 and plug it in. Negative 6 plus 5 is negative 1, and you can't take the square root of a negative 1 and then get a real number. Would be an imaginary solution. So this seems to work. And any number bigger than negative 5, like say 2. 2 plus 5 is 7. Square root of 7 is, well, the square root of 7. It's an irrational number, but it's a real solution. So this seems to work. Let's look at another one. Here we have the quantity 2x minus 8 in the denominator of a fraction, meaning it's really read as 1 divided by the quantity 2x minus 8. There's a problem with dividing by numbers. You can't divide by 0. That's one of the rules you learn in algebra, which means that this whole denominator, 2x minus 8, cannot be equal to 0. So we can set something up saying that 2x minus 8 cannot be equal to 0. This is a restriction that's imposed upon our denominator. So if we can solve for what x can't be, 2x cannot equal 8, and therefore x cannot equal 4. There we have it, the one value of x that we're not allowed in this function. So to write this in interval notation, it can be anything from negative infinity up to 4, okay, not including 4, and then everything from 4 up to positive infinity. Notice I drew a little union sign here. It's every value in this interval and every value in this interval, okay? There we have it. So what happens if we start combining things like square roots and rational functions? Okay, well, I have two different domain restrictions. The first one being in this numerator, 9 minus x has to be greater than or equal to 0. Let's solve for that one first. First domain restriction. 9 minus x has to be greater than or equal to 0. I guess for notationally, you guys are used to seeing x on the left side, so I'll subtract 9 from both sides and then divide by negative 1. X has to be less than or equal to 9. Okay, that's just the restriction under the square root. We also have 3x in the denominator, and recall our denominator cannot equal 0. So our second restriction is that 3x cannot equal 0. Otherwise, our fraction would be undefined. Divide both sides by 3, we'd find out that x cannot equal 0. All right, so we have two restrictions. X is less than or equal to 9, and x can't be 0. So when we collect all of the values of x that would work, we start off at negative infinity, and then we stop at 0 because it can't equal 0. And then we pick up from 0 all the way up to 9, which it can equal, and there's our domain. Any number between negative infinity and 9, inclusive of 9, but not equal to 0, would work for this function. So there's our domain. All right, let's look at more crazy stuff. We have the cube root of x plus the square root of x squared plus 4. let's take a look at each of these individually, each of these terms individually. Let's start with the cube root of x. Is there any number that we can't take the cube root of? Recall that the cube root is a function that allows you to use negative numbers. You can take the cube root of -8, it's -2. You can take the cube root of 0, it's 0. You can take the cube root of any positive number, any negative number, 0. So this doesn't have a domain restriction. So we're cool with this. We don't need to worry about that. Let's move on to this guy. It's a square root function. Square root functions your inside have to be greater than or equal to 0. Okay, so if we subtract 4 from both sides, we get x squared is greater than or equal to -4. Well, it's kind of a relief because if you square any number, you'll end up with a positive value, and a positive value is always going to be bigger than -4. I challenge you to find a value of x that you can plug into x squared where it would be not greater than -4. There's no negative values for x squared, so it'll always be greater than -4. This little inequality here has a solution of all real numbers, so there's no value of x that is restricted here. What that means is that this has no domain restriction and this has no domain restriction. There's no domain restriction in the entire function. No value of x would get you in trouble algebraically. So as weird looking as this function is, there's no value of x that there's a restriction for. You can plug in any value of x into either of these and end up being completely okay. So its domain is all real numbers. Let's look at one more little guy. It's a rational function that has both the square root and the denominator are all, I guess, part of the denominator. Alright, so we have two restrictions on this thing. First of all, x squared minus 1, the quantity has to be greater than or equal to 0 because it's under a square root sign. And secondly, your denominator cannot equal 0. So we start off with a restriction that looks like this. X squared minus 1 has to be greater than or equal to 0 because it's under a square root. But it can't really be equal to 0 because then our denominator would be undefined. So x squared minus 1 has to be just greater than 0. If it was equal to 0, then we'd have a bad fraction. Alright, so we can solve this by adding 1 to both sides. So x squared is greater than 1. To solve for x, we need to square root both sides, but be careful. When you square root x squared, you end up with the absolute value of x is greater than 1. Absolute value of x being greater than 1. Absolute value of x is a piecewise linear function. The left side of the piecewise function is the opposite of x, so that's greater than 1. The right side of the piecewise function is positive x, and that has to be greater than 1 as well. If we solve, we'll get x is less than -1, or x is greater than 1. This is already solved on this side. Alright, so our domain, right? X is less than -1, so all the values from -infinity all the way up to -1. And x is greater than 1, so we would start from 1 and go all the way up to infinity. This is actually an OR statement, so let me just write the OR here. X is either less than -1 or greater than 1, so it would be the union of the two and not the intersection of the two. Alright, and that's all that I have for you, so hopefully you are a little bit more confident on how to find the domain of a function algebraically.